So, we will come to lecture series on advanced linear algebra. I will continue with the applications of the primary decomposition theorem. We have already seen when a linear operator T defined over a finite dimensional vector space, when the minimal polynomial is product of linear factors, then the operator is having a block diagonal matrix representations, that is Jordan canonical form of the operator. We have seen it. That we have used, that we have seen using the one interesting results, that is when you use the primary decomposition theorems, we have seen that any linear operator defined over a finite dimensional vector space can be written as a sum of a diagonal matrix and a nilpotent matrix. Then we have used one interesting results related to the nilpotent operators like this. I mean, if you consider T be linear operator on a finite dimensional vector space V of index k, then T has a block diagonal matrix representations in which each block entry, diagonal entry is Jordan nilpotent block, and that will be denoted by say capital N. It is like that, and each entry will be basically Jordan nilpotent block. We already defined what do you mean by Jordan nilpotent block, that is basically some sort of shifting operators we have defined. In that block diagonal matrix representations, there will be at least one Jordan block, nilpotent block in of index of order k. Since the Jordan nilpotent block, if it is of the index k, means it also have to be order k, and all other entries will be of order less than or equal to k. The total number of Jordan nilpotent block n will be exactly equal to the nullity of the operator T. Specifically, the what should be the total number of Jordan nilpotent block of a specific order, say order I, that will be uniquely determined by relation that the number equal to 2 into mi minus mi plus 1 minus mi minus 1, where mi is the basically nullity of the operator T to the power I. So, based on this concept, one can have a block diagonal matrix representation of a nilpotent operator. So, for examples, if I consider here, I have taken two matrices A and B, it is basically you can say the matrix representation of a nilpotent operator, say one is a T, another is a U. We have seen that we can see it here. See, let me consider first the A, let the matrix representations of a nilpotent operator T on F5 cross 1 be say capital A, whereas I can consider say another operator who is also matrix representations with respect to standard order basis, of course, on F5 cross 1 is a capital B. Now, for the case of the A, let us see how the operator T whose matrix representation is A have a block diagonal matrix representations. So, that we can, this is again some sort of examples we are using to utilize this to check the theorems what we have discussed right now. So, we see here first we have to calculate the what is the nullity, I mean index of the A, please. We can see A to the power 3 equal to 0, that is the index of A is 3 and a to the power 2 is not equal to 0, but a to the power 3 equal to 0, that is index of A is 3. So, it is a nilpotent operator or nilpotent matrix please here. Similarly, you can check that b to the power 3 equal to 0, but b to the power 2 not equal to 0. So, implies index of b is 3. So, I have taken two matrices A and B, which are basically matrix representation of two operator with respect to standard order basis, and we see here both of them have the nilpotent index is, say both are having 3. Now, question is what is the block diagonal matrix representation? Okay. So, here I have since the operator is defined over space F5 cross 1, that is over a space of dimension 5 and index of A is equal to 3. So, one nilpotent block of index of order 3 will be there and index of A is 3. So, at least one Jordan nilpotent block of order 3 will be there. Now, the question is, next question is, how many Jordan nilpotent block will be there please? That depends on the basically nullity of the your operator T or matrix A please, and number of total blocks is equal to nullity of A. See, A is having two non-zero rows which are also linearly independent. Since rank of A equal to 2 implies nullity of A equal to 3. So, there will be exactly 3 not Jordan nilpotent block in the block diagonal matrix representation of the A. So, let M A denote the block diagonal matrix representations of A or T. Then M A will be equal to diagonal, the one block will be of order 3 since the index of A equal to 3. So, I will have like this 0 1 0 and other there will be 2 more. So, 2 more is basically of index, I will say that I mean of order 1 and 1 only, that is 0 and 0, because the total number of block has to be exactly equal to 3. So, this is the basically block diagonal matrix representation of the operator T or matrix A please. Now, what can you say about the matrix B? For B, we have rank of B equal to 3, rank of B equal to 3. So, implies that nullity of B equal to 5 minus 3 equal to 2. So, total number of block must be equal to exactly 2. So, this implies if I denote the MB, denote the corresponding block diagonal representation of the matrix B, then MB will be equal to diagonal one entry block diagonal entry has to be a block of order 3. So, certainly 0 1 0 0 0 1 0 0 0. So, one will be like this and other one will be of order 2. So, this means that 0 1 0 0. So, this is the block diagonal matrix representation of the B, please. Okay. Now, we have seen when an operator minimal polynomial is product of linear factors, then we can have Jordan canonical representations. But what can we say when the minimal polynomial is not product of linear factors? How to handle that situations? So, it is like this. Let T be a linear operator on a finite dimensional vector space V over a field say capital F. Let P denote the minimal polynomial of T over capital F, where P equal to something like, let me consider P1 power R1, P2 power R2 and Pk power Rk, where Pi are monic irreducible polynomial over F. In this case, is it possible to have a block diagonal matrix representation of T? Answer is yes. Then how to do it? According to primary decomposition theorems, T will have certainly a direct sum of invariant subspaces. But what will be the invariant subspaces? For this case, we are going to discuss that one, please. So, for this, let me introduce a concept of cyclic subspaces. Let T be a linear operator on a finite dimensional vector space V over the field capital F. Let 0 not equal to alpha belongs to V be any element. let ZW, okay, Z alpha T denote collection of all elements like F T alpha, where F is polynomial, F is polynomial function over the field capital F. That is, I can say, I mean F belongs to capital F of, say, like this, polynomial function like this. So, this means that if alpha belongs to Z alpha T, then T alpha will be there, T square alpha will be there, because I can consider polynomial as a x, polynomial as x square. So, this implies alpha, T alpha, T square alpha all will be in Z alpha T. In fact, this set is a subspace of vector space V. This set is a subspace of V. So, how it is subspace you can easily prove by using a condition that if beta and gamma belongs to Z alpha T, so that C times beta plus gamma also belong to this ones, where beta is basically some sort of F1 T of alpha and gamma will be basically some F2 T of alpha. So, both will be again, so that is the polynomials, that C times F1 plus F2 is a polynomial over the field capital F. So, it will be again inside the Z alpha T. So, in that way we can show that this set is a subspace of the vector space. Not only that, say I will say that let K is the smallest positive integer such that T to the power K alpha can be written as linear combination of preceding elements, that is or alpha, T alpha, T square alpha and T k minus 1 alpha. So, that implies that T to the power K alpha equal to, one can write down say something like A k minus 1 T k minus 1 alpha minus A k minus 2 T k minus 2 alpha and like this minus A 1 alpha and minus, I can say that A naught alpha. So, this implies t to the power k alpha plus a k minus 1 t k minus 1 alpha plus a k minus 2 t k minus 2 alpha plus a 1 alpha plus alpha. Okay. So, this is equal to 0. So, this implies that if I consider f of t alpha equal to 0, where f of t equal to t to the power k plus sigma a I and t to the power k minus I equal to 1 to say k. So, one can write down like this, that is f of small t is equal to t to the power k plus sigma a k minus I and t to the power k minus I equal to 1 to k. The polynomial which annihilate alpha. Not only alpha, I will say that this f t, this implies this f t is the least degree polynomial, such that f t of even z alpha t, okay. So, this is equal to 0, this is equal to this one. Here also we can see here alpha t square alpha and t k minus 1 alpha is a linearly independent subset of z alpha t, which also spans subspace z alpha t. So, this one also I am giving as a homework, you can check it that this is a basis for the subspace z alpha t. In particular, if the restriction of t to if I denote the t alpha, if the restriction of t on z alpha t as t alpha, then f of t alpha equal to 0. In fact, the minimal polynomial of t alpha is f t. The matrix representations, the matrix representation of t alpha with respect to order basis, say B equal to alpha t square alpha and t to the power k minus 1 alpha. So, I am writing t of alpha, if I consider t alpha is equal to what? T of alpha, I mean t alpha of t alpha basically, that is equal to t alpha. So, this implies that the corresponding if I did C denotes the corresponding matrix representation of t. So, let me denote that matrix representation T alpha with respect to order basis B equal to suppose C matrix, then C matrix the first column will be the image of alpha under T alpha when you express as a linear combination of this basis element, take the coefficient and then the transpose. So, T alpha will be basically okay. So, I am getting what? And second element will be like this. Okay. So, it will continue up to we will have 1 and the last one will be your T of Tk minus 1 alpha, that is equal to So, if you see these expressions, then take the coefficients, then I am getting minus A naught minus A 1 and it will be minus A k minus 1. Okay. So, the matrix representation of T alpha with respect to order basis B equal to C. So, this is called here C is called as companion matrix of polynomial your f, okay, f t place. So, the matrix representation is here is basically companion matrix of polynomial f t place. So, we have seen that here if I consider a non-zero element alpha and if I consider the all the collection of the f t alpha, then it is subspace and it is of course another thing is that this subspace here z alpha t is also T invariant, because element are of z alpha t is equal to something some sort of g t alpha. So, certainly T of g t alpha will be also inside the z alpha t. So, that is I can say z alpha t is also T invariant place. Apart from that, here alpha is called a cyclic vector place, and z alpha t is called as cyclic subspace of vector space V place. Why alpha is called cyclic vector? Because all the elements of z alpha t is basically linear combination of the element of alpha, t alpha, t square alpha, t q alpha like that. So, this is called the cyclic, that is why it is cyclic, alpha is a cyclic vector place. Now, this concept will help us to basically split the space V as a direct sum of cyclic subspaces, and this proof is very lengthy proof. So, this proof I will leave it on you as a self study or homework. You can try, if you have any difficulty you will definitely discuss this proof over the tutorial class. So, now let me write down the one nice results where this concept of cyclic subspace has been used and how the space is decomposed as a sum of cyclic subspaces. Okay, so we see that when you consider a non-zero vector alpha, then we can write down we can introduce a cyclic T cyclic subspaces Z alpha T. Now, based on this spirit, there is a one result which is very classical results, and of course, following this result there is also final another interesting result which is basically talk about the block diagonal representation of the linear operator defined over a finite dimensional vector space. This result in terms of lemma is saying like this: say T be a linear operator from V to V, where the minimal polynomial of the operator T is say p to the power n, and P is a monic irreducible polynomial over the field capital F on which V is defined. Then V will have a direct sum decompositions of T cyclic subspaces. I mean there will be some vector alpha 1, alpha 2, alpha r such that V will be exactly equal to T cyclic subspace of Z alpha 1 T, Z alpha 2 T and Z alpha r T. T generator of the Z alpha 1 T is p to the power n 1, for Z alpha 2 T is p to the power n 2 and Z alpha r T p to the power n r, where n equal to n 1 greater than equal to n 2 greater than equal to n r. So, one can have a direct sum decomposition of the space V, where subspaces are T cyclic subspaces, which are of course invariant T invariant, and the T annihilator, I mean the least degree monic irreducible polynomials of the corresponding cyclic subspaces are basically p to the power n 1, p to the power n 2 and p to the power n r please. Okay. So, here in this theorem it is also saying like, if you consider, see this decomposition is not unique, it is saying that there will be another decomposition also, but even if you consider the any other decomposition of V in T cyclic subspaces, the number of components will be exactly same, the set of T annihilators also will be same. Thus, T has a unique block diagonal matrix representations. This result says basically if you consider linear operator on a finite dimensional vector space V with minimal polynomial is p to the power n, then space will have a direct sum decomposition of T cyclic subspaces by introducing R cyclic vectors alpha 1, alpha 2, alpha r, and the corresponding T annihilators the p to the power n 1, p to the power n 2 and p to the power n r. Now, using these results, this lemma basically, when the minimal polynomial is not only one irreducible polynomial p, it is a product of suppose many irreducible polynomials. So, in that case the operator will also have a block diagonal matrix representations, and of course the space will also have direct sum decompositions, which is like this. Okay, so in the first case, when only the minimum polynomial is p to the power n, the block diagonal matrix representation will be MT, which is basically block diagonal matrix whose diagonal entries are C1, C2, Cr, which are basically component matrix of p to the power n ni please. Already we have defined what is the meaning of the component matrix of a polynomials. So, if the polynomial p is known and p to the power ni is also will be known. So, based on that only you can calculate the corresponding Ci please. Now, the generalization of the above lemma, which is coming in terms of these theorems, is saying that if T be a linear operator on V to V with minimal polynomial is say p equal to p1 to the power m1, p to the power m2 and ps to the power ms, where pi is the monic irreducible polynomial, then T has a block diagonal matrix representations mt equal to diagonal, I mean the diagonal entry will be C11, C12, CR1, C21, CR up to C2R2 and like that, where Ci is the companion matrix with respect to polynomial pi to the power mij, where again same relation holds good, that is mi equal to mi1 greater than equal to mi2 greater than equal to mi please. So, this both the result, I mean the lemma as well as these theorems, the proof of this both the problems are basically I am leaving on you because it is very lengthy. So, you can try, if you have any difficulties definitely we will discuss over the tutorial class, or you can ask by email. If you have any difficulties to understand the proof, we will definitely clarify it please. Now, let me apply these results to find the block diagonal matrix representation of different problem please. So, first let me consider So, I have taken examples like here V is a vector space of dimension 8 over the field capital F, and T be linear operator defined over 8 whose minimal polynomial p is equal to p1 into p2 square, where p1 is equal to t to the power 4 minus 4t cube plus 6t square minus 4t minus 7 and p2 is equal to t minus 3. So, we have to find the possible block diagonal matrix representations of T. Let capital A M denote block diagonal matrix representation of T. So, certainly there will be one diagonal element, at least one diagonal element which will be the companion matrix of P1, and other one will be companion matrix of t minus 3 whole square, because the dimension is 8, p 1 having degree is 4. So, if I consider companion matrix of t minus 3 whole square, then if I consider 2, then 2 plus 2 is equal to 4 plus 4. So, this is one possibilities. Other another 2, other one will be at least will be t minus 3 whole square. So, the possible block diagonal matrix will be like this. I can say that one is like this, I can say MT is equal to diagonal of companion matrix of your t to the power 4 minus 4t q plus 6t square minus 4t minus 7, then companion matrix I can say of this is t minus 3 whole square, that is equal to t square minus 6t plus 9, and again it may be the companion matrix of same t square minus 6t plus 9, because 2 plus 2 4 plus 4 equal to 8, because t is defined over this one. So, this is one possibilities, and other one may be diagonal of companion matrix of first one will be there minus 40 q plus 60 square minus 40 minus 7, then component will be 1 will be there t square minus 60 plus 9, other one we can consider companion of t minus 3 and component of t minus 3. So, that 1 plus 1 is equal to 2 plus 2 4 plus 4 equal to 8. So, we see there are the two possibilities when possible form of the block diagonal matrix representation of the your operator T here. So, we know how to calculate the component matrix of these ones So, if I consider C1, because we will have only one term C11, I am writing like this thing, this is basically 0 1 0 0, then 0 0 1 0 0 0 0 1, and then minus 7 minus 4. So, plus 7 plus 4, 7 4 minus 6 and plus 4. Yeah. So, see the component matrix are related to the P1, and your C21 I can say 0 1 minus 9 plus 6 and C22 also, which is also equal to same as C22. And so, in this way you know how to calculate the component matrix. So, you can have a block diagonal matrix representation of the operator T, please. So, that is all basically the applications of the primary decomposition theorems, because these theorems what we have used, I mean we have written mentioned here, this is basically based on above lemma as well as primary decomposition theorems. So, I hope you are getting some idea about how to decompose the space as well as operators using primary decomposition theorems, and how to get a Jordan canonical form. And actually this representation what I have done it here, this is called the rational canonical form. This is called the this is called the rational canonical form of the operator T please.